This video is for those who are absent today. Today we discussed how to make a buffer, which is what you will be doing in the lab on Thursday. This is the pre-lab that goes along with the making a buffer lab, which needs to be completed before the lab. So you'll be looking up the molar masses of these chemicals and figuring out the conjugate acid or base or both, if it's amphoteric. You will also be looking up the Kas of these acids on your Ka table, determining their pKa. Now the general rule is if you need to make a buffer solution of a certain pH, you need to choose an acid whose pKa is within plus or minus 1 of the pH. So for example, this acid has a pKa of 3.29. This would be a good acid to make a buffer if your buffer solution needs to have a pH between 2.29 and 4.29. Or for example, if I were asked to give you a pH, if you were asked to make a buffer with a pH of about 3, you should choose an acid whose pKa range is between 2 and 4. So any acid whose pKa is between 2 and 4 would be a good choice to make this buffer. This is one such acid that we could choose. So we're gonna go ahead with this example and use HNO2. That would be the acid of choice. But we also need to make a buffer with its conjugate base. So if we remove an H plus from that acid, its conjugate base is NO2 minus. However, normally this is in salt form, meaning you need a spectator cation going along with that. I find it's easiest to choose sodium. This will be disguised as sodium nitrate. Now, there's a difference between the 3.29 and the pH of 3 that we were asked to make. And the difference could be made up in the ratio of base to acid. So we're going to solve for what ratio should the concentration be in. We can use the Henderson-Hasselbalch equation and solve for that ratio of the base to the acid needed. So I'm going to solve for this. The pH of my buffer is 3. The pKa of this acid is 3.29, and I'm going to solve for that ratio. To do so, I'm going to subtract 3.29 from both sides, and I'm left with this. To get that ratio, I need to undo a base 10 log. To do so, I'm going to raise both sides to the power of 10. By doing that, the log goes away, and 10 raised to negative 0.29 is equal to the base over the acid. We get 0.51. Please know that sometimes this number is positive, and that's okay. You do not have to make it negative if it's positive. If it's positive, just do 10 to the. All right, so this should be really a ratio. To turn this into a ratio, we're going to put this over 1, and these represent the molarity of the base to acid that we need. It's a ratio. It doesn't mean we need these exact molarities, but molarities that reflect this ratio. So, for example, we only have 0.1 molar of the acid available. So we don't have 1 molar, but we have 0.1 molar of this acid available. What molarity of the base solution should we have? Well, to reflect this ratio, we're going to need a 0.051 molar base solution. All right, now, that doesn't mean that we can just go online and buy a 0.051 molar base solution. Oftentimes you have to make it. And if it starts off with a solid salt, we're going to have to make it fresh using our volumetric flasks. And we want to make 100 milliliters of it. So we got to figure out how many moles are we going to put in this flask to make this molarity of our base. So I have 0.051 molarity over 0.1 liters. I can solve for my moles of base needed. 0.1 times 0.051 will give me 0.0051 moles. Now we don't have a mole machine, of course, but we have a balance that can measure out that many moles. So I need to convert that to grams. And this is the sodium form of it. So if I do a T-chart, that would give me 69 grams per mole. So I would need 0.35 grams of the NaNO2 needed to make that solution. So what do? I would take my 100 milliliter volumetric flask, fill it halfway with water, dump in this much base. By filling it halfway, I have enough room to mix it and swirl it around. And then after it's mostly dissolved, I can fill the rest of it so that the bottom of the meniscus hits the line. Then you'll have your base solution. You will also have your acid solution. And if you mix equal volumes of each, the ratio is maintained. So if you have 100 milliliters of your base, you will mix that with 100 milliliters of your 0.1 molar acid. And yes, they will get diluted, but by mixing equal volumes, the dilution will occur so that the ratio of their concentrations is still the same. So technically, after diluting, you'll have 0.02 55 molar of the base to 0.05 molar of the acid. And that's okay because that still reflects the ratio of 0.51 to 1.